Welcome. Today we are going to talk about semiconductors and the devices we can build out of them. Yeah, let's get going with this. In the last lecture we discussed a lot about the meaning of the Bloch's theorem and how that raised or gave place to the existence of the first Brillouin zone, the reciprocal space, and many other concepts, and from there we more or less built up, although not very formally, but still built up the idea of band structure and these curves that relate the k vector that is essentially the momentum, or what we call the lattice momentum, of the electrons moving in the lattice, in the semiconductor, and also the energy state. So, the first thing we more or less depicted was that, for example, we discussed a lot about insulators and metals or conductors, and we even mentioned very briefly the idea of semiconductor. So, as we said, formally a semiconductor is probably something closer to an insulator rather than a conductor or a metal, in the sense that it has, at least when we are talking about an intrinsic semiconductor, and we will say exactly what that means in just a few minutes. It really is a material that has a completely full valence band, a completely empty conduction band, and it has a band gap, and therefore what we have is formally something that is more like a an insulator. And what I drew there is what we call the bands, and I just put there the valence band and the conduction band. Thinking again in terms of a semiconductor, the Fermi level will be somewhere in between the two bands, or the Fermi energy, and essentially what we will see is that all the states in the lower band that I drew there are populated, so they are occupied, and all the states in the upper band, the conduction band, are empty. And a good part of the last lecture, what we did is make arguments of why, for example, this first level here and these, any other level somewhere there, and any other level somewhere within a band, actually do not only differ in terms of their energy, but also in terms of their k vector and therefore their momentum, or their lattice momentum. So, but we basically gave arguments of why, at least to first approximation, there should be a dispersion relationship between these two variables, the k vector and the energy, that should look more or less like a parabola, at least to first approximation. And here I will draw another parabola that is facing down, and we will come to that in just a few minutes, which will represent the other band, the valence band. And essentially these particular levels that I put there in different colors represent different points in this parabola. So this one could be either these or these, and this one could be either these or these. And let's not worry too much about the fact that we have two at the moment. Let's think just in terms of one. And the same applies to the other band. So we could find a level somewhere here at the top of the band, which we can in principle relate to probably this state, or this combination of energy and k, and perhaps another level somewhere around there, which we can relate to these, and another level somewhere there that we can relate to these other for example. So what the difference between all these densely packed energy levels that we show as bands on the right hand side is essentially that the energy, the eigenvalue of the energy is different, so they have different energies, but they also have a different combination of kx, ky, and kz, or in general, let's say just k, and this is more or less the way we see them. Okay. Now the conduction band, I put it as a parabola facing up, and the valence band, I put it as a valence as a parabola facing down. And this is because I will introduce a new idea that you will probably have heard before, but still, and is the idea of holes. So in semiconductors, in general, in solid state materials, there could be, in principle, two types of charge carriers. One are the electrons. So the electrons are well, just the electrons that propagate through the lattice, and we've discussed that a lot. And in principle, it could be holes. And what is a hole? So let's assume that we have a completely a perfect insulator, like in a scheme like the one I'm drawing here. And so this means that all these levels over here, all these levels down here, are populated, and the ones over here, these ones are not populated. So what happens if, for some reason, I remove one of the electrons over here? Let's say this one. So this one I either excite it to the conduction band, or I simply remove it from the material. That will leave one empty state that will look like if it was a positive charge. So it's although it really is the absence of an electron, it will look like if it was a positive charge. And in the presence of an electric field, and let me just draw here. Let's assume that electrons are more or less equally spaced and so on. And if I remove one of them, so if I, let's say, erase this one, what this leaves behind is this vacant position that looks like a positive charge. So if I apply an electric field, let's say in this direction, this means that the electrons will feel a force in this direction. Okay, so this electron will try to hop into this vacant state. This one will try to hop into this vacant state. And what will happen is that effectively this hole, when this electron hops over here, what will happen is that the hole will look like if this positive charge have moved to this position. And eventually this one will move over to this position when this other electron this other electron tries to hop there. So effectively we could think of this current as being an enormous ensemble of electrons all moving together and more or less pushing each other to try to occupy this state. Or we could think of this conduction in terms of the of this hole or this vacancy that we have here moving in the opposite direction. So it's effectively a positive charge or a positive a charge carrier that moves as if it was a positively charged electron, more or less. Not exactly, because since most of the states are occupied and this hopping and feeling the hole that is there is hard, because most of the electrons have neighbors and it's not easy for them to move. These these holes will not be very agile in moving. They will not move as easily as, for example, an electron would move in the conduction band, where it has lots of many states where it can gain energy and accelerate and so on. So in general, holes, although holes are the absence of an electron, we treat them as carriers, and we treat them as if they were slightly awkward, not very agile carriers. So they move a little bit slower, and they have more difficulty moving, and that is related to the fact that it's actually the ensemble of electrons moving in the opposite direction. But it doesn't matter. I mean, we can see it either way in terms of modeling, and it's much easier to deal with just a few holes than trying to deal with all this ensemble of electrons all pushing each other just to fill the vacancy and try to hop into this hole. So in that sense, that's why we put the second parabola, the parabola that corresponds to the valence band, facing down, because we can think of this parabola as the dispersion not of the electrons but of the holes. And since the holes have a positive charge, and the minimum energy state in this case, so in the case of an electron, let's say we put an electron in the conduction band, the minimum energy state for an electron will be this position, okay, the lowest point in energy. But if we think in terms of holes, what we need is all the electrons, not the hole, to occupy as low states as possible. So the valence band will tend to have let's say this state occupied, and then this, 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 and then this. And if we just removed one of the electrons, the whole will be basically just this vacant state, which is in the highest, so it's the state of the highest energy. And so the whole will occupy the highest energy level, which is actually all the electrons occupying the lowest, all the lower energy states. And that is why we put it facing down, so that the whole, for example, will actually, the minimum energy of the whole will actually be this top state with the highest energy for an electron. Okay, great. So now let's think in terms of how these semiconductors are used, how they are manufactured. And let's think of one of the most common semiconductors. Let's think of silicon. So silicon, as any solid, will form a lattice. So it's repeatable in space. What I'm drawing there is the position of the silicon nuclei, and not just the nuclei, but let's say the atoms. And silicon happens to be a material in the group number 4 of the periodic table. So this means that it will have its core electrons, all the completely full bands and so on will be occupied first with all the core electrons, and the valence electrons, the electrons that fall in the last band, will be 4 for each one of these silicon atoms. Okay, so this one will have 4, this one will have 4, this one will have 4, and of course it's an infinite lattice, so this goes on in 3 dimensions, right? And so we have something that looks a little bit like this. So we have these 4 electrons that are each one of the atoms supplied. So as we put together the crystal, more or less, each one of these atoms will provide 4 electrons in the valence band. And each one of these electrons we know, they will not see the potential of its individual atom, but more the potential of the entire lattice. So, and that is why they can occupy all these bands and everything that we have said so far. So effectively, the quantum system is the macroscopic crystal, and the electrons, what they see is the potential of the entire macroscopic system, this silicon crystal. Okay, so it so happens that the situation is such that exactly what we said earlier happens. So when we put all four valence electrons in this crystal, exactly the valence band is full, so all the states of the valence band are occupied, and all the states of the conduction band are free. And something we could potentially do is replace this silicon atom um, with an atom that comes from the group 5. So just for a second, let's have a look at the periodic table. Silicon is here, okay? It's in the group 4, so that's number 4. And we said, what if we take an element from group number 5, which would be this column, so nitrogen, phosphorus, and so on. So if we do that, and I'll go back to my previous slide, what will happen is that this group 5 atom will provide not 4 but 5 valence electrons. And so we will have these 4 plus one additional one that is more or less breaking a little bit the perfect repetition of all these silicon crystal. However, the electron will see the potential not just of its own atom or just the first neighbors or the vicinity. What the electron sees is the potential of the entire silicon lattice, which in principle is infinite. So we have many silicon atoms in all three directions. So what this electron sees, and is very important to realize, is all these electrons, all 5 of them, are indistinguishable from the rest of the electrons supplied by the silicon atoms originally. So they're all the same. It's just that we've managed to put one too many, okay? And what this implies in terms of the bands is that, okay, I'll just draw very quickly here, again, the conduction band, the valence band, and what this implies is that the structure or the levels, the solution of the Hamiltonian will essentially still be the same, because we're just putting one atom in a very, very large lattice of silicon atoms. And so, okay, it will be, strictly speaking, it will be a little bit different, but in the end, the potential that we have to solve is still the silicon potential. And so as we said earlier, the valence band, the conduction band, and all of these states over here are occupied, and all of these states over here are were free. And what happens when we introduce this additional electron that I'm putting here? So again, I'll just draw here the band structure, and what happens is that all of these states over here are occupied. Plus now one of these states is also occupied with this additional electron, this one electron too many that we have put now. So with this, we have managed now to, strictly speaking, convert this insulator or semiconductor insulator into a conductor. For, strictly speaking, it's a conductor. It might not be a very good conductor, because it will only have one electron that is free to move. However, strictly speaking, this material now has the possibility of conducting electricity due to this one electron. Of course, something we can do is we can not replace just one, but one of every, let's say, million of silicon atoms. So we will have roughly 1 million silicon atoms and one group 5 atom, and then another 1 million of silicon atoms and one from the group 5, and so on. And this would probably still be a large number of group 5 atoms. So we will have thousands or even hundreds of thousands, or I don't know, or even millions of them in a sample. So this means that the bands, we can choose, but depending on how many of these dopants, we call them, these group 5 atoms, how many of these states we populate. And therefore we can control very precisely by just controlling the purity of the material that we use initially. So we put just pure silicon plus a very well engineered, determined amount of group 5 dopants, and with that we can decide exactly how many electrons we want to put per unit volume. And this allows us basically controlling the conductivity of the material to whatever we want it to be. And we can decide where to put the Fermi energy, for example. We can decide, okay, we fill the band down to here or down to here, or so just by playing around with the number of group 5 atoms that we introduce in the lattice. So this is one of those things that one can do with a semiconductor. One could also do the opposite. So one could let me erase this. So instead of putting group number 5 atom, let's now think of a group number 3 atom. And this means that this one will only contribute with 3 electrons, but there will be one electron too few in this case. So there will be an electron missing. And again, what this means is that instead of having this picture that we have over here, what we will now see is that, let me just make a little bit of space here. What we will have is that now the conduction band and the valence band, in the case of the 3 dopant, is that if we just put one single atom, again, this state will be vacant, and all of these states will be full. Again, strictly speaking, this means that now what we used to call the valence band, strictly speaking, should be called the conduction band, because it's no longer full. We don't change that. I mean, we keep calling it the valence band just for convenience, because really the conduction band is the one on the top, and this one will really be a conductor that will conduct electricity by holes, not by electrons. So these, let me just label them. This is the case of the group 5 dopants, and in principle we could do the same. We could replace one of every 1,000 or every million or every, I don't know, a large number of silicons by one atom from group 3. And in this case, what will happen is that something a bit more complicated than this will be seen. So now, instead of having just one, a few of the highest energy levels of the valence band will be vacant, and therefore this material we can control the whole conductivity or the conductivity due to holes in this material. It's something that is very important to bear in mind is these materials are still electrically neutral. The fact that they can conduct is because they have either occupied or unoccupied states in a single band. However, they are electrically neutral in the sense that group 3 or group 5 atoms will contribute the same number of protons as electrons. So they will not be charged materials. They will be materials that are electrically neutral in terms of charge, but that will have these properties. They will be have a controlled number of either full conduction band states or empty valence band states. And by controlling these, and this can be controlled to an extraordinary degree of precision, we can determine very, very well the degree of conductivity that the material will have. So, although intuitively what I just said in the previous two slides is correct, strictly speaking, it might be a bit misleading. So let's draw the valence and conduction bands again. So we have this densely packed set of levels that we call the conduction band. We also have the valence band, which are lots of levels packed there all together by valence band, conduction band. And when we add a dopant, and here we're thinking of this coordinate as the position. In the position where we put one of the dopants, let's say we put a dopant right here. Okay, so what this will imply is that if it is a group 5 dopant, what will typically happen is this group 5 will not, strictly speaking, donate, and that's why they're called donors, an electron to the conduction band. It will produce, in most cases, or in a good number of cases, a single level that lies just below the edge of the conduction band. Again, this is the case of the group 5 materials that provide additional electrons. Now, this level is usually so close to the conduction band that simple thermal excitation, a few milli-electron volts or a few tens of milli-electron volts, will be enough to promote the electron that lies here and that was weakly bound to the group 5 material into the conduction band. So this process of promoting here happens naturally at room temperature. So in that sense, the semiconductor, we really are, at least at room temperature, providing electrons that are injected or promoted into the conduction band just naturally. The same happens for group 4 electrons. They usually group 3 dopants. So in that case, what happens is usually provides an empty level. So I will put this empty level very close to the edge of the valence band. And what will happen is that in that case, again, thermal excitation will be enough to populate these electrons, to populate this level. So electrons that were somewhere around here will quickly fill the hole and leave a hole behind in the valence band. And so all I said is at least intuitively correct in at room temperature. Although strictly speaking, it might not be true, because sometimes the levels of these dopants do not really fall within either the valence or the conduction band. But typically, they are close enough to the edges of the corresponding band, so that for any practical purpose is true. Okay. Now, having clarified that, what we should now try to understand is what happens if we, for example, can produce what we call a joint. Okay, great. So before we go into discussing joints as such, I'll just introduce a new way of calling these semiconductors. So semiconductors that are doped with excess of electrons are called N semiconductors. So these ones are materials, for example, silicon that has been doped with let's say group 5 materials, or the other way of calling them is P, and that's for example silicon plus a dopant from the group 3. So these ones are materials with deficiency of electrons or with excess of holes. So the N and the P comes from the negative or positive types of carriers. So these ones are N materials are typically are materials that conduct by the motion of electrons. P materials are typically materials that conduct by the motion of holes. And yeah, well, we call them this way when building joints and more complicated structures. So regardless of the fabrication techniques, which we will discuss in a later session, let's assume that one can produce a piece of semiconductor in which, let's say, 1/2 of the piece is N-doped and the other half is P-doped. This means that in this case, over here, there is these ones will behave as conductors, both of them. The N1 has an excess of electrons, so it will basically conduct through the motion of electrons, and the P-doped material will be a material in which there is deficiency of electrons or excess of holes and will conduct through holes. And when we produce a joint, what will happen is something very interesting. Let's try to have a look at the what happens here close to the joint. Okay, so when we look in the microscopic scale, and let's think, yeah, we're talking about 1 micron around the joint. What will happen is over here, when we get far away, let's say over a micron, let's use a different color. I'll just draw an imaginary line there, which is just to tell us, okay, this is roughly 1 micron, plus minus 1 micron, or plus minus half a micron from the joint. What will happen there is that we will have, I mean, the electrons that come from the dopant are there, the holes over here are also there. And here near the junction, what will happen is some of these electrons, the electrons that used to be here, will recombine with holes on the other side. They are close enough that they see each other, and the electron says, oh yeah, okay, there is a hole there, which is basically an empty electronic state in the lower band, and will make a jump and try to fill these lower energy states. So the total effect is that this region here, which we call the depletion region, or the depletion zone, will not have carriers. It will, although the lattice centers and everything are still there, the dopants are there, the atoms are there. Strictly speaking, all the electrons and holes will cancel each other out, and we will have a little zone of, again, roughly 1 micron, but it changes a little bit depending on the semiconductor, in which there will be no carriers. Okay, so this material, this joint, or this very thin layer around the joint, will not be conductive. And what happens is that whenever, I mean, of course, this means that here we have some electrons from this side, from the N side, will have migrated into the holes of the P side, and this actually creates an electric field. So there will be depletion of electrons in this side and of holes in this side. So effectively what we have is a positive and a negative, slightly positive and slightly negatively charged region. So all in all, what we obtain is a, as I said, a positively charged region here, negatively charged region, and this produces an electric field that points in this direction. So when we usually had, and let me draw here, so this is the valence band and the conduction band. And this usually is two bands that are independent of position. In this case, electrons on one side and the other, and holes in one side and the other of the depletion region will have different energies, because this electric field effectively corresponds also up to a potential that is a function of the position. So what we have in the end is a pair of bands that, in the absence of doping and so on, you have the conduction band and the valence band, conduction band. But in the presence of this joint, what occurs is, due to this recombination of charges and the appearance of actually charged layers on both sides of the joint, what we end up with is a band band diagram as function of the position. Remember, this is not as function of the k vector that now looks a little bit like that. So the distance between the two bands remains constant. So the band gap, this band gap doesn't change, but the two bands are now disaligned, and this is what the bands look like in the case of the vicinity of the depletion region. So you will have the joint somewhere around here in the middle, and the depletion region is somewhere in between these two lines. So when you form this joint, what you have is that. And remember that this side is the N doped side, this is the P side, and what this implies is now that there's actually holes in this band here. There are electrons on this band here, and essentially there are no carriers in the depletion zone in between. Okay, so now what happens if now, for example, I'll draw again this joint. So I'm thinking of drawing the material itself. This is the N side, the P side, and we will have this depletion region here around the joint. And what will occur now if we apply an external bias? So if we connect this thing here to a battery, for example, and how will this thing behave? And what we eventually find out is that, let's say that the battery is connected as I show it there. So let's say this is the positive pole of the battery. This is the negative pole of the battery, and the positive pole of the battery will try to attract electrons. So the excess of electrons. Remember, the N doped side has electrons here. So these electrons will tend to move in this direction. The holes that are on the other side here are positively charged, and these ones will try to move in this direction. So the holes will try to move in that direction, and all that will happen is that this depletion region, if anything, it will get wider, and the misalignment in between the two bands will get greater and greater, and there will be, I mean, since there is a depletion region where there's no carriers, what we will obtain is something that looks basically like an insulator. It will not conduct electricity. However, what happens if I will just erase the battery. I will now put it in the opposite direction, and let's see what happens. So now we will have the minus sign here, the plus sign here, and in this case, electrons on the n side will feel repelled, so they will move towards the junction, and also positively charged holes here will be repelled from the positive pole of the battery. So in this case, the carriers from both sides will be pushed into the depletion region, and at some point the depletion region will be closed, and electrons will start flowing and finding holes on the other side. So in that case, what happens is that we will go from the unbiased situation that looks like this, where you have the N side, the P side, and the depletion region here in between. And when you bias it in the correct direction, what happens is that this misalignment between the two bands, which at the moment looks like that, will be inverted. So at some point they will level up, and from that point onwards, what we will have is, sorry for the colors, what we will have is this case, right? When I mean, at some point they will be exactly leveled, and from then on the joint will start conducting, and that's because now electrons that are here on this side will tend to flow in these directions. In this direction, holes that are here will tend to flow in this direction, and as soon as they start occupying the depletion region and overlapping with each other, there will be recombination of the electrons here and the holes, here, and this means that electricity will start flowing through this junction. So the opposite scenario is now that the bias is in the opposite direction, and now the alignment or the misalignment of the bands occurs in reverse, and so if anything, now this slope will now be bigger. This jump between the energy in one side and the other of the junction, and this means that now electrons over here are being pulled away from the junction, and the holes over here are also pulled away from the junction, and since the junction has no carriers, there will be no conduction. So this device, as simple as it looks, is very, very useful. It is what we call a diode, and diodes are these devices that allows us rectifying, for example, the current. So if we have a fluctuating current and we want to just keep the positive side, for example, we can insert a diode, and if we put it in the correct direction, it will let current in one direction but not the other. And there are tricks as well in which you can use 4 diodes, for example, to get the absolute value of a fluctuating wave, and so on and so forth. I mean, this is not an electronics course as such, but the idea is that you now understand how a diode operates. So another very interesting device that we can build with the same idea, more or less, is what we call a transistor. So a transistor is now, instead of a 2-layer, is a 3-layer structure of semiconductors. So what we have now is a piece of semiconductor in which we introduce, for example, N-doping, P-doping, and N-doping again. And in this case, I mean, if you think about this, this is a lot like having 2 diodes connected back to back. So if we apply a voltage in between here and here, it doesn't matter in which direction the positive and the negative sign, one of the two junctions will always be reverse biased, and therefore this device does not conduct any electricity. However, if the region in the middle, so the p-doped part in this case, is thin enough, what we can achieve is the following. So we could, in principle, have again, I will draw the entire transistor here. Let's think of the intermediate layer being relatively thin, and by relatively thin I mean it should be maybe a little bit bigger than the depletion region, but not much bigger. So we're talking about 2, 3, 4 microns. It's just a few microns, so that basically the two depletion regions are almost touching each other, or even completely touching each other. Pn, and what we can add here is now an additional source of voltage. Sorry. Okay, if we do this, what will happen is that now this junction here that I will draw in white, this junction here will no longer be reverse biased. If we apply the voltage in this way, the negative charges here, the electrons in this region over here, will be attracted towards following a path like this. Okay, so going into that power source that we have there. However, some of these electrons, I mean, since the intermediate region, which we'll call the base of the semiconductor, is thin enough, many of these electrons will acquire enough kinetic energy in this direction that they will not be able to bend their path and go up towards the base connection, but will actually just go across the entire base and land on the other end side. And in this case, these electrons will now see the other power supply and try to follow this other trajectory. So in the end, by applying a little bit of current, just very few electrons will be able to bend their trajectories and go up in the base connection over here. And most of the electrons will manage to go across the first barrier that I painted there in white, and cross all the way into the N side, as long as the base layer is thin enough. And this means that in principle, by turning on and off this voltage here, we can basically regulate the flow of current in this other arm. So a transistor can be used as a current control of as a device that controls the flow of one current based on another current. So by applying or not applying current into the base, you can switch on and off the flow of current in the other two terminals. And this is very useful because with these one can electrically control the flow of electricity in other circuits. So this allows us controlling from a very small signal here in the base relatively larger currents that happen in between the other two between the two other terminals. So again, transistors are super important nowadays technologically. our telephones and so on. I mean, the processors that are inside our computers, the televisions, I mean, pretty much anything that you find around you that is electronic has them by thousands or millions or thousands of millions and even sometimes billions of them. And they form the base of both analog and digital electronics. So this is one other device that is possible and that gives us two functionalities. One is using one electrical signal to switch another electrical signal, and the other one is using a small electrical signal to produce a much larger electrical signal in the other side of the loop. And this opens up the possibility not just to digital electronics, because it allows us switching on and off and doing logical operations and so on, but also allows us making amplifiers and all sorts of different very interesting electronic devices. Okay, so now we will discuss a slightly different device, which is also a transistor, and is what we call a joint field effect transistor. So imagine you have a cylinder, and let's say it's made of n-doped material, so n-doped semiconductor. And let's assume that we can remove a ring around this cylinder. So something a little bit like that. So it's something that looks a little bit like a donut all around, and we fill that little bit with p-type semiconductor. So if we look at the cross section, if we make an axial cut, what we will see is a device that looks a bit like that. So we have the p-doped region over here. We have the n-doped cylinder. So this is the n part. This is the p part. And let's say what happens in the vicinity of this joint. So the same happens as in the case of a diode or the other transistor. We will have a region around the joint in which there will be no carriers. So we have a depletion region over here and a depletion region over here. So this means that with a bit of material that we removed from the P part, plus this extra micron or two of the depletion region, what we will observe is that we have a very thin channel region in this part. Okay, so yet this is not completely closed, and in principle, if I connect a battery or a voltage source over here, a current will establish in this region, and current will flow through the circuit, even if the channel is relatively small. Okay. However, if I now put, let's say, a battery, and let's say we put it in these polarities here, so the minus sign is over here. So the minus sign will attract the holes that are in this little bit here and here. Remember, this is a ring around. So the holes will be attracted towards the connection in the outside, and therefore the depletion region will just get bigger and bigger as we apply more and more voltage. So at some point, the depletion region can get big enough that it could, in principle, completely strangulate the channel. So by applying a negative voltage on the terminal that corresponds to the ring that we call the gate, we could, in principle, start reducing the conductivity of the channel. and we can modulate that. So we can control by using a voltage on the base pin. We can control how much current flows through the other two terminals. So this is in a sense similar to what we saw. Now the logic is a little bit different. Now the transistor is normally on, and you can start lowering down its conductivity until you completely strangulate and you turn it completely off. However, this type of transistor is also very useful. It's called a joint field effect transistor, and it has some differences as well. First of all, since the joint over here, so this joint between the N and the P type, so the P type ring and the N type central region of the cylinder is biased in reverse voltage. There is going to be hardly any current, or there will not be a current flowing here. So this is purely a voltage controlled change in the channel size. So there will be current flowing over here, at least unless we apply a voltage that is large enough that the transistor will completely strangulate, so the channel region. But what we will achieve is a voltage controlled current flow, which is a little bit different to the bipolar transistor, that is the one we just discussed earlier, because that one is a current controlled current. So there is a little bit of current going through the base that controls the current going through the other two terminals. Well, here is a little bit of voltage but no current that controls the current that goes between the other two terminals. And this is the main difference between the bipolar transistor, that is the one that looks like a sandwich that we saw a few minutes ago, and these joint field effect transistor. And it's called field effect transistor because it's basically just controlled by the electric field and not by the current flowing in the case of the gate terminal. Okay, let's talk now about another type of transistor. So this one will have a slightly different configuration. So let's assume that now we have a piece of p-doped semiconductor. So I will draw a large piece of p-doped semiconductor, and let's assume that we can make little holes and fill them here with n-type semiconductor. So what will happen is that we will have a depletion region formed around the joints, as you know from the diodes. So we have this area that has no carriers, and essentially we will then deposit a thin layer of oxide over here. So it's a thin layer of oxide, right? Oxides are typically very good insulators, so they don't conduct electricity. So this separates electrically the P semiconductor from the contact that we will put here on top. So let's assume that we can then put a thin layer of metal on top, and then another electrode, and let's assume that we put these two other terminals. So there's one terminal to each one of the two N connections, and we have this insulated terminal close to the region in between, which is p-doped. So what will happen now is that, of course, the p-doped region has holes in it. So there are hardly any electrons, and basically what you find in that region are holes. In the n-doped part you have electrons, and in the depletion regions you have essentially no carriers. So what happens here is that if we apply a voltage, let's say we put the minus or the ground on this side, and a plus side of a battery or a power or a voltage source on this side, what happens is that this this joint on this side here is directly biased. So this one, the depletion region, will get smaller and smaller, and eventually this, so to speak, diode will try to conduct, will be available to conduct. However, in this other side, the opposite happens. So basically there you have an inverse biased diode, and the depletion region on that side, on this side over here, will actually grow. So in the end, you have no conduction in between these two terminals. If we now start increasing the voltage, if we start increasing the voltage over here, and let's say we can extend this contact all around into this region over here. So another plate is connected here. Basically, an electric field will start forming between these two plates, which will be pointing in this direction. This means that some electrons will be pushed into the material from this side and will try to travel in that direction, and these holes over here will travel in this direction, and so on. Some of the electrons will reach the region here, not next to the oxide or insulator to semiconductor joint, and those electrons will recombine with the holes in that region. So at some point, what will happen is we will have a depletion region there, because there will be the electrons and the holes will recombine, and we will completely have a layer here that will also be a depletion region. It will not be caused by a joint as such, it will be caused by this electric field. If we keep increasing this electric field, what will happen is, I will erase here now, what will happen is that this depletion region will move, this depletion region will move now down to here. So we will have a zone in which there will be no carriers, but some electrons will actually be attracted up to here, and these electrons will form a channel that will connect completely the two terminals on the sides. And at some point, if the voltage on the gate on this terminal here in between is high enough, the channel in between, a conductive channel in between the two N regions, that is also an N channel, will be formed, and there will be conduction between these two. And if we keep increasing and increasing the voltage on the gate terminal, the amount of electrons available in this channel will be bigger and bigger. And with this, we can control the flow of current between the two terminals here and here, just the same as we do on other types of transistors that we have already discussed. The really nice thing about this type of transistor is, well, it has two very good aspects. One is the insulation between the gate terminal and the semiconductor is super good. There is absolutely, if in the joint FET, in the joint field effect transistor, there is hardly any current, because the gate is basically a reverse biased joint. In this case, we really have an insulator in between the terminals, so the current flowing through this terminal is really negligible. There's no current going in or out of that terminal, so it's very high insulation. So just by putting a voltage there without consuming any power whatsoever, the channel can be closed, and then the circuit can be closed, and the transistor can be turned on and off, and also the current can be regulated in between the other two terminals. The other aspect is that this is a very the geometry of this type of transistor that is called a MOSFET, that comes from metal-oxide field effect transistor, and again is because the way this channel is formed is due to the fields that we introduce in the device. This is a nicely scalable device. Many of these can be integrated in very small sizes in a single wafer of semiconductors. If you have a wafer of semiconductor and you can, let's say, drill these little holes and put the N-type material, for example, or not drill the holes but just dope selectively some regions of the P-type semiconductor with N-type. You can put millions and millions of these and just interconnect them with little wires, and this is the way integrated circuits and all the digital logics and processors in your computers and your phones and everything work. So this is actually the type of transistor that is used for digital electronics and for integrated electronics. So with this, I want to conclude the presentation from today. I just want to add that there is a really excellent book for these. Simon C. is the author, and the book is called Semiconductor Devices, Physics and Technology. It's a really nice book. It's easy to read. It's very didactic, so you can have easily access to this book without too much previous knowledge of advanced solid state physics. There is another book by the same author which is called The Physics of Semiconductor Devices. So the title is a little bit different. That one is super high level. That one is not so accessible. This is really a solid state hardcore book that is for very advanced level. So of course you are encouraged to have a look at that one as well. But in order to understand the function of all of these devices, this is a really good book which I recommend. So with that, we will conclude the session for today, and in the next session we expect to discuss a little bit more about now the optical properties of semiconductors and how we can make a series of other devices that are called optoelectronic devices, in which the interaction between electrons and light actually makes them very useful for other applications and so on. So thank you very much, and I hope to see you in the next session.